Now that we've got a lot of the details out of the way, we're ready to actually solve some problems. We're limiting ourselves to linear regression, so the class of functions that we're searching over are linear combinations of basis functions that we choose, and the error criterion is the square root of the sum of the squares of the individual errors. Given that framework, the optimization can be recast as a linear least squares problem. Let's see how that's done. Let's start with one of the easiest cases, where the approximating function class is all affine functions. I've written that like this: f sub ab of x is ax plus b. In terms of the basis function description, the first basis function is x and the second basis function is 1. Linear combinations of those become ax plus b times 1. Using the n-point training set, the mismatch, or the errors in fit at each point, are the function evaluated at the x-coordinate minus the y-coordinate. Written out, that's just axi plus b minus yi. That's clearly a function of the choice of a and b. Remember that regression is going to choose the best approximating function from this class. In vector form, all the components of the error can be written as a matrix n by 2 times the column vector of the parameters which are to be chosen. Notice the top row gives ax1 plus b, the next row gives ax2 plus b, and so on, minus the y's. Since we're using the squared error criterion, the goal is simply to choose a and b to minimize the norm of e. Remember, the norm of e is the square root of the sum of the squares of all the entries of a vector. Consequently, the regression problem looks like this minimization. Minimize over the parameters. In least squares, we'd call that x. The norm of an array which is known, in least squares we call that a, times the parameter vector, in least squares we call that x, here it's a and b, minus another fixed vector that we know, b. This is exactly the linear least squares problem, and we could solve that using either the backslash operator or p inverse. One thing to notice is that the letters have all been switched around. In this module on regression, x and y are data. In the least squares module, x was the unknown variable. In the least squares module, a and b were data. In this module, a and b are the unknowns. So I apologize for that, but that's fairly traditional notation. That's why I've drawn these arrows here to make the connections for you. In this case, the matrix A and the matrix B are known. They come from the training data x and y. The vector x is really the unknown parameters a and b that parameterize the approximating function class, and of which we're trying to pick the optimal one. Let's look at the code for just a very simple function that implements this. There's the problem. I'm calling it affine fit. The x data and y data are input arguments, and the parameters a and b, along with some measure of the error, are the output arguments. Comment: fits an affine function y equals ax plus b to the data given by x data and y data. The code really should check the dimensions of x data and y data. Here, for simplicity, it's written as though both are column vectors. It should check to make sure that they have the same number of elements. I'm not going to do that for space reasons. The only steps are to set up the least squares problem, solve it, and then return the output arguments. N is the number of elements in x data. R is this matrix, the x data horizontally concatenated with a ones vector. We use the backslash operator to solve for the least squares problem. Using the backslash operator, it's r backslash y data. That gives the optimal 2 by 1 vector consisting of the components little a and little b. Pull those out for return. And finally, let's define error to be the norm of this minimum mismatch. So r times opt param, that's a and b, minus y, exactly as shown.